Yes. Ah, okay, perfect. Cool.
If you move here,
They won't see me.
appear, we will the camera.
Ah, okay. I'm trying because I'm walking a lot usually when I'm talking, so I'm trying to not walk that. Ah, okay, in case you will move that. Okay.
Okay. Okay, thank you very much for coming. We have here today again Francesco Bertolotti from Luke Università Cattaneo. He's a postdoc in his third year, and he gave a intense social meeting yesterday, and today he will offer another kind of things in a seminar format. I forgot to say yesterday that he also wrote a book. I didn't say it yesterday, but he also wrote a book about
These are the
the artificial intelligence of Dostoevsky.
Exactly.
Yes, the artificial intelligence of Dostoevsky. Well, the floor is yours, Francesco.
Thank you very much. So, hi again, and I'm Francesco Bertolotti. Today we are going to talk about social system simulations. So, fantastic is just a reference to J.K. Rowling book, but I'm not sure there. So, fantastic, we'll judge at the end. This is me, but Pablo already introduced me. From this, you understand, you can see the only new thing that you actually can see that I'm not photogenic, so I guess that we can skip. And yes, I'm doing complexity stuff, that's fine. And it starts with a warning about this topic. So, first thing first, of course, I'm going to talk about something, of course. But always remember, let's remember that, like for the fallen caryatid of Rodin, the one in the sculpture, research is like victory in defeat. So, like, they are the ends of the top of the iceberg, what I'm going to show. But for these, there are all the tons and tons and tons of hours that ends up with a failure, like we all know as research is. Second point, I will focus on results also, of course, but we'll focus more on idea. I will try to make an overlook on the different topics I'm working on these days. They're kind of wide, so I wanted to actually pinpoint many things to try to stimulate a conversation, to get some ideas, some sparks. I guess this is the main point of an event like this. The alternatives were just to take a paper, a single research, and deep dive on that. But I wanted to try to make like a more general overview. And third, I will mention explicitly as much as I can, but all of this wouldn't be possible if I would have collaborators. So different co-authors, different people that help me in all this stuff. So thank them in advance, but I will also mention them explicitly time to time. So let's start for what will be the topics of the presentation. First, I will talk about my recent work, which is not so recent anymore, something I did in the last year and a half, let's say, on emergency care units. So it was pinpointed by policymakers. We did some kind of systems analysis with emergency care departments. Then I will talk about an epidemiological extension of the health for all problem, in a way not only talking about the extension, but also what very cool dynamics emerges after and how do we study that. Third, I will discuss some work on cliodynamics I've recently started. And finally, I will just make a sum up of all the other things I'm doing time to time. And of course, this is remembers a little bit Michael Scott, which is playing parkour. I know that, so let's highlight. So, complexity science for emergency care unit. Why? I don't know if you know, the Italians know for sure, that's why they are living here maybe, but Italian healthcare system is at the bitter end right now. We had a great system 25, 30 years ago. progressively became worse and worse and worse for many different reasons. Aging population, because of less fundings, privatization of the healthcare, many. But the critical situation makes a point which policymakers ask support of universities sometimes, because they need to do a better, erogate a better system, better services with actually less resources, or the same resources. So how to do that? You need science, let's say, in general. So in this case, they ask specifically the Healthcare Data Science Lab of the Luke University, which I am a research affiliate, or I don't remember exactly the name in English of my position there, but I'm collaborating with them for a few years right now. So they contacted them to actually get a better insight how to manage their system. And they contacted me for this job. And together, we actually try to give some insights and some proposals to policymakers using complex systems. And what's more, we actually discovered something in the meantime. So we generated, and we are generating some papers. So let's start from the main point, which is there are too many people in emergency care units, in a specific area, we were talking about this in a bit, compared to the one that the system can manage. So the first thing that we will need to know is actually why the patients are going in a specific hospital and not in the other. Or better, we cannot actually know exactly why it is, but we actually can interpret how the patients, where the patients decide to go, the decision-making process of the patients. So we're starting from this, and we're starting in a process that was completely data-driven. So let's not start theoretically, let's start from the data. And then start from the specifics of each patient on one side, that which have the data on. And for example, taking into consideration something in this kind of problem has never been taken into consideration. So how serious is the condition of the patient? And of course, we will need to know where they're living, and because the geographical proximity will have an effect, of course, but still again, data-driven. So we didn't theorize before. We start from the data, and then we see if we could find something that actually makes sense. And something that takes into consideration also the stochasticity of the patients. We can even find a good law for patients' behavior, but we cannot find a law which is correct 100% of time, of course. So this is the overall idea that we had. Actually, it's like the idea came to me during a flight on an airport. The airplane was stuck. I was waiting for a while. I was a friend of mine, and his 3 months old baby, which cannot stop crying, of course, because it was a storm in the airplane. So instead of sleeping or reading, I start working, and that's where this came from. So thank you, Alessandro Dainotti, for that. In the paper is thanked, actually. I put thank in this. So the idea is start from a classic gravity model. So the preference towards a specific structure, if you're a resident in CTK, and you have to go to the hospital at the city I, or the hospital I, the preference could be the inverse of the distance. That makes sense. I mean, this was actually widely used in literature from the 80s, and it exists for much longer, of course. And but then the intuition was, let's add some features on that. Explicitly, let's add some features that make sense, that are explainable even to the manager of the hospital, and he will hear that and say, fine, I mean, it makes sense that the patients decide this way. I can trust your model. So the point is, let's suppose that the patient prefers all the time, prefers an hospital which is bigger, which has more beds. Actually, one could argue that the number of beds of the emergency care unit and the hospital overall can differ, but they have a correlation 0.99, so it makes no sense to diverge. So the bigger is the hospital, the more likely you are to go in there. Fine. And then the more serious you are, from 1 to 5, because there are 5 different codes. I mean, 1 to 4 we say in this case, because the last one was the black, we remove it. 1 to 4, which is white if you are not serious at all. Yeah, green if you are serious but not that bad. Yellow, red if you start to be serious, and yellow if you start to be serious, and red if you are critical. So you have 4 codes, encoding these codes into an ordinal number, 1, 2, 3, 4, and elevate the number of beds to this. So the more serious you are, the more you are likely to prefer a place which is bigger, which intuitively, if it's bigger, is more likely it is able to perform more kind of cures, okay? So we start from this, and of course then we compute the probability that each, compute easily the probability that each patient will decide to go to a specific hospital, and we decide to test this. Of course, before we have tested the simple gravity model, and it was not working fine. 60% of the patients were going somewhere else, so it makes no sense to use that. And then we test it. And we test it on what? Data is king. So we start from the policymaker that asked us to do this. So the ISST Satlaghi, which is a public hospital between Milan and Switzerland. We have from there, this is a nice map, this is the map. We have from there 3 years of data between 2019 and 2022. So we remove from this data the data of during the COVID, because there's something different. Then we arrive with 225 86 patients, on which a certain amount are resident in this area. So we didn't consider the patients which are not living there. We consider only the patients living there, because we want to see the attraction for the patients actually living on the territory. Then in the model, we consider also the one after, but we'll discuss it later. So we have the data. We actually implement this. It's very simple actually to test. It took 20 minutes, 30 minutes, very quickly. But you find out that the distribution of the patients to each hospital overall fits a lot. So that simple rule was enough to guarantee, once we have fitted the 3 parameters, that actually the hospital, okay, were served each by more or less the right amount of people. We were kind of happy about this, because the average error, the maximum error was 215, okay, so the highest error for a single hospital, and the mean error was 123%. Good, this works. A very simple law that explains nicely with data a real life phenomenon. Cool. But this misses something. This misses the fact that, yeah, but we want to know actually if the people from each specific city that are going to one place to another, if this reproduce or not. So we check it, of course. We build a network where the nodes are the cities and the links are the patient's movement. And we know that in some of these cities there is an hospital, so we consider that as the focal point. We build the real world, the network with the real world data. Sorry, I missed the click. Where the colors are the majority. And we actually see that the people are going more or less close. There are some hospitals that has a wider range, some other has a smaller range, but that in the real data, in the simulated data, this is respected. So even looking at the 2 networks, we see that there is an actual comparison. But this was not enough yet. Why? Because we want to actually see if the single people would decide in the same way. Is it possible to check this? Yes, of course. We have data, so we can try that. We were a little bit skeptical, but overall, this is the real data. And you can see now with the arrow going down, you see the simulation data, you will see the simulation data overwrite the real data. So look now, okay, you see that The map is changing a little bit, but more or less the distribution remains the same. So more or less the people that we are allocating to one city, to one hospital, are more or less the same. And more specifically, we got a mean error or around 2% on the overall system. And for the cities with population is greater than 7,000, which is actually a definition of city in the Italian system. If you're below 7,000 inhabitants, it's town. In that case, you only have 0.7%. So very good. That's working. We actually presented this to the people that asked the work. They were very happy about this. They are using these and other things we are doing to decide where to put the next structures, of course. And also, at that point, we wanted to try to publish. And it was recently accepted on Scientific Reports. I mean, today I have to pay the bill. So yes, it was a bad moment about this, yes. And but still, we need further confirmation. Like, this is working. Data show that this is working just fine. And we were very happy about this. But there is still one but that we want, and we are trying to check, that we want to see. So is this because people from Varese regions is boring and decide in a predictable way? Or this is a more general law? We need to check. We don't know yet. So we need to make analysis on different Italian territories. We have collected data from 14 departments, so we are checking these weeks. And of course, we are also checking because Italy's system has changed the color codes. So now it's not only 4 codes of severity, it's 6. So we can check if this holds even with 6 levels. And of course, with an external collaborator, we got the data from Austria. And I'm trying to see if in Austria this is also valid or not. Because it will make sense if we show that this is not just for Varese or not just for Italy, but it's something that is more general. Of course, then one could argue this can valid only in Western countries, so on and so forth. But still, for a practitioner, it's a very good result. Still, the generalizability by now looks sensible. Okay, so at that point, we have 2 directions of analysis to do. The first is we did all of this to be able to build an agent-based model of the healthcare system. So the part in which we actually build an agent-based model of the system, and then the second work, which is trying to use a complex systems perspective to manage better and measure better also the overcrowding of a healthcare system, which is actually in literature and practice right now is a little bit of a disaster. Okay, so let's start for the first one, okay? Yeah. Yes. Remember the number, I have to check. Yeah.
Is that making the hospital bigger makes the thing worse. Because you increase, you double the number of beds, and then you increase the number of people going there beyond that doubling. So is this alpha exponent is bigger than 1?
Okay.
When you double the beds, you increase the probability more than the double to go to the hospital. So making the hospital bigger is a bad decision.
Depends on which, I agree, but depends on the purpose. Like, I don't know anything about healthcare management, like underground. I agree on this, of course. And the point is, for what I understood, for what the policymaker needs, they need to have a network of places where people could go, which are close enough and which will avoid to overcrowd the bigger place. Yeah. So you need to make places which are big enough to attract the proximity, even when the code is not, when the severity is not very, very low, even for middle severity, the higher severity have to go to the central hub because that's the only one they have the resources to manage. But the other, you need to find a combination for which most of the people is going actually, most of the people around the new structure is going actually there. So you already mentioned the number of beds. This is on theory, because the number of beds that we are used, of course, depends on the number of people.
Understand.
They don't have any people, but it's, yeah.
Okay, thank you.
You're welcome. Okay, so the first regards the overview of the agent-based model we have built for that. The idea is to start from a full territory. So simulating first the towns, very simple and model way, of course, not simulating the roads and the traveling things of the town. Simulate the patient generation of the town according to the data that we have. Then make the location decision, which will be made according to the rule we have just seen before. Waiting in queue for the treatment for each patient, which is an agent generated, we wait in queue for treatment, and then it will be treated by professionals there. In order to do this, we have to make a set of modeling hypotheses because still we need to simplify the system, otherwise it's not going to work. So the first thing that we model is the fact that the patient is genderless first. Second, we didn't trace the individual because we didn't have data about that. So the data that we have available from the hospital and the hospitals were not allowed to recognize if a single patient came 2, 3, 4 times in the same time. And the patient cannot leave the queue, which is a strong assumption, but it's necessary. So if I'm going to an hospital, I see a queue of 20 people, I not just saying, okay, now I'm going another day. They stay in the queue. I mean, I would say this, but they're not. And each patient have age, health, severity and residency, and a specific condition. And then the decision regarding where to go is made according to the law we've seen before. Cities are connected to each other through traveling distances and not, of course, Euclidean distances. Same city travel is 5 minutes, which makes sense because of the size of the cities, which are very reduced. This is not like an area with cities of 400,000 inhabitants. The biggest one, Varese, has 28,000, the second 20,000, so it makes sense. And if you're not resident in the area, you're allocated to a special city that we are going to see later how we define that. And in the ICU, there is no like special path, there is no special departments, it's all together, and there's no any specific organizational structure, which is something that management people really care about, but for these, in this case, at least for the first version, was not really necessary. And then the personnel, we decide to not adopt any distinction. So one person is one person, because overall in emergency care unit is very peculiar, so they are doing a lot of things, first. Second, because hospitals do not really have the data about who is working that, which was something that surprised me. If you ask the people that are talking to us, administration, of course, have the data, but apparently they're not really talking. So we got this distinction. They're not specialized and everybody is good the same, and they're not resting during their turn. So given all these hypotheses, which are strong, but we suppose reasonable, and we have to actually generate the patients to make a process which was explainable, because we need always to explain the guy that commissioned this, why we take a specific decision. And on the other side was reasonable regarding the kind of patients was generated. So first, we assign a specific probability for generation of patient according to the triage code, so the severity, according to the specific day of the week and the hour of the day, according to the city and the age range. Why so? Because we have enough data that we can actually get a good probability of generation even for this, a probability that makes it work, as long as we are generating it with a person. So we are generating the specific patient, and then since we divided the age in age range of 5, we assign with the severity, using the statistics from the data, the proper age. Once we have the age of the person, we assign, according to the frequency that we get from the data, the related, from the statistics from the data, the related pathology. There are like 30 different macro pathologies, and we actually assign that. Okay, there is a return. Can you...
Estoy conectado, pero estoy bien.
It's just enough to turn off the microphone. Okay, and thank you. And after we have the pathology, we are using also this to combine from the statistic we got from the data to generate the treatment time. And at the end, we have our patients with all the characteristics. The treatment time is computed in advance because we assume that all the doctors are the same. So they're curing all the time in the same way, which is not exactly true, but if there's enough occurrences, we could suppose like this. We have to assign a proper city to non-resident patients. So we apply the rule before, and we get the non-residents. We are supposed they're coming mostly to the hospital 0, which is at the border, east border of the region, southeast. And so we basically try to shot around with some kind of correcting algorithm, not just random, to find if these are the hospital, the place where the distance between where it was supposed to be and where it actually is was the minimum. And we found out, this is funny, that is just in the Monza Autodrome. If some of you follows Formula 1, you know that the Autodrome is just beside. The good news is that it's in Monza, which is one of the biggest cities around in that area, which is not inside the area. So it also makes logical sense. Well, we have a place where we can assign a non-resident and still provide them a proper arrival to the proper hospital. Then we have calibrated the model, and we are calibrated in a way which we got exactly the frequencies of this is the time for the time of treatment for each combination of patients, for each age range, and for each severity code. So getting all this combination, we're getting a different distribution, and we actually can find for all of these the distribution that fits the best and generate it in this way. So we have collected all the data for each different combination, and when we assign one of these, we can generate it according to the specific distribution and the parameters that we have fit towards that. And then we did this for the individual calibration of patients. There was most of this, but I'm presenting one. It was a very long and tedious, not tedious, I had fun actually, but it was a very long process. The second was to calibrate the system with the global variables, because if we calibrate with the global variables, then we are able to see if more or less it fits all together. And thanks God, overall, this is an example, the system fits. So we can see that more or less the behavior is kind of similar. Then there are like some differences. There is higher variability. I use the mean here, but more or less we can see that we are able, with not a higher error, to calibrate the whole model. And once I've done that, tell me. Horizontal is the hour of the day, sorry. So this is the trend of the day. The mean for 1 hour, 1 month of simulation of real data. And so basically the results we got are interns for this. We didn't publish yet this paper. I mean, we have the model done, but we wanted to generate more results and explore the behavior a little bit better and then to publish. We just generated the results for the policymaker. And if the average queue length starts from 17.5, which is the AZs at the moment that we actually got in contact. And now the AZs is 11.6 because they build some new structure by themselves. So before reading the results of the work, what he found is that we actually made some kind of exploration of the possible combination of the different new emergency care units. So if we position in one new place, what is going to change? How is going to increase the number of people average in the queue? And we found that the 2B that the ISST wants to have, so what they are planning to do, will decrease of 12%. The decrease that we are proposing them would improve the decrease of another 10% of what they're doing. So we'll have a 10% less of queue, more or less. And we have found also, this is the most critical thing actually, that if they would wait a second, or they would ask us in advance for a combination, the actual better positioning will take a much better result than what is going to be now. I mean, now we're gonna, in the best case scenario, the queue will be on average on the 1 month 9.2. If they took the combination that we will have proposed, starting from the beginning, they will have 7.5, which is actually almost 20% increasing. This, of course, does not take into consideration something. For example, it doesn't take into consideration the fact that these new buildings were made with the next generation EU funds, so they have to be done in advance. But takes into consideration something else, which is that as a boundary, we ask them where they have already a structure where they can build an hospital, because of course they cannot build an emergency unit from scratch. I mean, they could, but they won't have the funding of that for sure. We knew that. So there only were like 20 places, 15 places, something like this. I remember the exact amount, which you actually can put something. And this already takes into consideration. So is on the one side something good, because we propose them a new combination that would maybe increase the performance of the whole system, ceteris paribus in terms of cost. On the other side is a little bit of pity, because it could have been maybe done in a different way. So since time is tyrant, I will skip the overcrowding. And yes, because this is a little advanced, but yes. And go to the second point. So that was the part about healthcare management. So the enhanced gravity model and the ABM. Then let's talk about something which is very different, because it's totally theoretical, at least for now, which is an Elfarol bar extension with epidemic. This actually came from a note that I wrote a few years ago on a paper. And a couple of students of mine came to me one day, a couple of years ago, and they asked me if they could do something of things that I'm doing, because they like it. They stalk me on internet, and they like doing this kind of simulation things. They never did anything like this. So I take my notes. Oh, there is this. If you want to try, let's see how it's going. And actually, we did a kind of good job. And I mean, I hope they were also goodly supervised, but for sure they're very good. And it get totally out of our hands, because overall we will have 3 papers out of these. We were supposed to have like B1, but since you cannot submit, you can, but it's not smart if you want to do a little bit of career to submit one paper with a lot of things, which is long, 70 pages. At the end, we have to split at that. I'm not a huge fan of that, but okay. So I'm assuming that all of you knows the Elfarol bar problem. You know that? No? Okay. So the Elfarol bar problem is a problem theorized by, I have an angular memory, okay, but it came in my mind 1 second after I think about, by a scholar from the Santa Fe Institute in the 1994. And the idea was, if you have a bunch of citizens, a bunch of people that has to go each Thursday night to this bar, the Elfarol bar, to listen to some music, some Irish music, Brian Arthur, because was Brian, and some Irish music. And then you are, of course, he was doing this, but he wants to go because he really likes that. But he doesn't want to go if it's too overcrowded. So he has to try to assess using what he remembers from the previous iterations if people will be there or not. And everybody are doing the same. So this more or less would stabilize the system around with a noise around the threshold, if the threshold is the same for every people, of above which is not standable to be in the place because it's too crowded. So the idea is, let's take the affordable problem and let's add the fact that if they're attending, they can get infected with a disease. And so let's study the intersection between, so this is the scheme of the model, but okay. The intersection between the epidemiological part and the social part in this kind of setting. So we have a bunch of hypotheses, basically the classic hypothesis of Faraday model. So they're depending on the previous, their decision depends on the past, of course. So the memory they have of the previous time they went. There is a threshold attendance above which they are going. If they have expectation above which they are going, below they are not going. They are using memory to make prediction. And then some classic epidemiological assumption. So you get infected, you have a given time of recovery, you have a given time in which you're still. Maybe the last thing that we have, not new, but we have included, which is not completely standard, is the fact that we have that the contagious level decreases in time. So how CQR decreases in time. And most important, that you have one threshold above which you understand that you're sick, and so you're not attending the event, and below which you actually do not understand that you're sick, and you will attend the event, and a second threshold above which you can infect other people, and below you cannot infect other people. So the contagious threshold. So the intersection of these, I mean, we have experimented with Python and doing some sample analysis on the parameter space, but let's talk about the result because these things more or less is known. And what actually we have find out is, okay, we've seen these funny behaviors, there's a repetition, we find this kind of nice cyclicity around, was very scattered, very original, but okay, very scattered, original, not so important. After months, we thought that maybe they were important, but it took a while. And then that relationship between variables were kind of meaningful. Okay. And more specifically, okay, we got that there was this an infection probability to last until the end changes to the parameter space. And that different scenario could affect actually the fact that infection will lasting, of course. And there is an interplay between the epidemiological and the social perspective, especially in terms of the fact that when the threshold attendance would increase or would decrease, actually the mean, the probability of infection will be higher or lower, of the infection lasting will be higher or lower. So basically, if they will stand more the crowding, it's more likely the infection will last, of course. And if they will provide a different weight to memory, to the more recent memory, the infection will have a lower probability to last. Okay. But we have this, and we were more or less wondering, yes, but fine, nice. It's interesting, it's an interesting game and playing. We have some kind of things, we describe it better, of course. But then, is it enough? Or not? Can we do something different, better? And there is a famous Italian actor did a scene which was saying, yeah, of course not. Who cares about this? Okay. And the work is totally theoretical. The dynamics looks interesting, but it's understudied. I mean, oh, that scatters, fine, but we just left there. We didn't actually analyze that. And we want to be a little bit relevant for policymakers. We can find something like this, and we are not relevant for policymakers, for practitioners, while we are doing it. Otherwise, it's just for publishing paper and try to have a higher impact index. That's not part, I mean, it's part of the game, but it's not the purpose of science. So we thought, let's do something different. Let's do as would one of my musical heroes, Bach, do two variations. The first variation, let's try to analyze this cyclic behavior and see if we can get something out of that. And the second, which I don't think I will talk, let's talk about the policymaker. So the overall idea is to try to make a policymaker managing the epidemic and train it with some reinforcement learning. And actually for this, Pablo rightly suggested if I put Italian prime minister, you wouldn't understand the joke. That is half robot because it's AI. So he suggests me that I could put a picture generated by AI of your prime minister, so he will better understand him. But still, we're going to see only the first, and we're going to see in the way in which I'm kind of interested in this kind of game, especially to get some kind of cyclic behavior, getting the cyclic behavior out of data. And when I don't have any equation of which I can actually study, because I don't know the analytical treatment of that. And it's not complicated, but it's still way too complicated. I mean, for me to do a good analytical treatment. And I see that kind of rich. So the other idea was, can we actually study that in some way? And we tried to find a way. And the way we tried to find was the following. Getting the two variables that are here, so the number of people attending and the number and the number of people infected each time step. Getting all that, getting the maximum autocorrelation level for each of them, so that I will detect if there is a strong autocorrelation between both of them. Then at that point, getting the one which has a high level of autocorrelation, of maximum autocorrelation. At that point, of course, you're doing this, cutting maybe the transition states initial because of the transition state, because otherwise it will be too much noisy, the data. And then you find a given threshold that you're interested in, and you take only the simulations for which the periodicity is more or less the same, plus minus 1. So they are both high periodicity and both have the same periodicity moving together. So I'm assuming if I plot them on a two-dimensional plane, I will seek a cycle behavior in a certain way. And of course, this is not like a sufficient condition, fine. But maybe it was necessary, maybe we can find something. Let's check again. You never know in research where you're going, so let's try that. And we found a lot of guys like this. A lot of simulations have this kind of cyclical behavior. Well, a lot because we did 1,250,000 simulations. So even if just a small fraction satisfy the criteria, in that fraction, we actually will find a lot of cycles. Fine. Then we clustered them. There were like 3,000, so we're clustered manually. Because I mean, I had no idea what I was doing, so I wanted to see them. I wanted to actually see if I could find something new, if I could recluster, if I was doing something smart or not. So I didn't use any AI system. I did it by hand, just to check it. And we found some kind of different clusters altogether, which this is distribution fine. But the more interesting part is they have a lot of shapes which are repeated in time. And we can find in more and more and more and more time the same shape. Again, months for the autodrome for the people that follow in Formula 1. And because that's the same, so reversed L, I didn't really like it. And that was already interesting, the fact that there were many clusters and so on. But we wanted to do something more. Again, it was not enough. Is the number of people attending?
Yes.
And the number of people infected.
Okay, so it's the number of people attending and
Yes.
And another question: if somebody is infected, is not going to attend.
He's not attending. Yes.
Until several weeks or whatever.
He's not attending until his level of contagious gets below the threshold. If you want, And so, but you see here something that these are connected to each other. How? How do you connect something like this to each other? So again, a little bit of serendipity, as there is not enough. So the main point is, as it was mentioned, the book about AI, I'm spending, and you may notice yesterday, I'm spending way too much time playing with generation AI system. So since I was doing some RAG, basically for making system for students to access directly my lessons. So I'm recording, I'm transcribing automatically, and then I put in a RAG system. So I help, try to support them. I was doing a lot of cosine similarity between, of course, these vectors. So I thought, but if I encoded if I find the mean of mean of parameters for each cluster that I found, and I create a vector for each of them, and then I found the distance between each of the mean parameters value, space value for each of these shape, what I found this matrix, which is the matrix used to generate the previous network. Which again is something, maybe you told me that you already see this did in the 80s, sometimes happens, but it's something that I never seen it before, and that is especially interesting because you can get the transition from one cycle to another, to one shape to another, because they are connected. You can get this. By now, I think that the best way of getting the transition is not by creating a network. Network is more for representing it, but is try to get a better understanding on general. But still, like what we're done like this. And of course, then you can see specific shapes, read what is the mean of parameters and the standard deviation and the other statistics, and try to get an interpretation. Why, when this happens, when the other happens, if this is more desirable than the other, what should I do? What should I change in my system to get one point to another? Then, of course, I will need, and this is the main point, to test this also with real data, which we didn't do yet. But this is, I think, the case in which theoretical study provides you a good overview. So finally, a little bit of cryptodynamics. So Clio, the god of the muse of history from the Greeks. Dynamics, I don't have to explain, you know better than me. So again, this is a disclaimer. I don't think I will ever do this if when I was a child, I wouldn't have read Isaac Asimov, I wouldn't play Civilization, because where we came from strongly affects the research we are doing. And so when 15 years later, I found Sabine Roman, which is one of my closest or I guess, the one which I have the strongest scientific relationship, in a meeting at the CCS, the one held online during COVID, which was presenting these topics, of course I wanted to talk about what he has done, because I really like. And then again, also, I found other people, between also Pablo, that at the winter workshop last year, and again, meetings have, people have, doing research, they have generate nice idea. So there are like 4 things that we are studying with different people in different groups. I will just focus on the first 2 because the time is a little bit short. And the first is let's go directly to talk about. The idea came reading an history book I have on the shelf. I took it about the history of Carthago. You read the history of Carthago, it ends in 146 before Christ. Then, if you read the history of the early Christian era, the main city, one of the main cities of Christianity, or the main city of Mediterranean, was against Carthago, even was destroyed, because St. Augustine was there. Why? So I get this idea. Why? After that, I went to the winter workshop. They went to organize a group of people working on some topics, and I said, I have this idea. I actually remember thinking about that a few days ago. Someone wants to check. So we try to see if it's a matter of position on the network, is a matter of the resources available, or both. And so if what affects the success of each city in the Mediterranean trade network during the Iron Age, which is the moment it's going after the War of Troy, more or less. So the idea is that we have to get data, which of course is not trivial. You cannot just make it out. The cities were available on this from this lab from Utrecht that collected the populations of the cities and their position. The network, the trade network, was available on Orbis dataset, where the trade nodes. So actually Pablo cleaned that and provided. And the mines and oil pressed were present on the Oxford Economics Project, Oxford Roman Economy Project. And for the width data, instead, we got from a paper that we was waiting for actually the actual data, not scrapped for the picture of the paper, but we got for the paper from a couple of years ago. So given all of this, we have a bunch of resources. This is the wealth production in different areas around the empire of the around the Mediterranean. These are the nodes in the association with the Voronoi polygons. So we can associate different area to the closest city. And this is the combination between the red dots, which is the size in the population of the city, and the blue dots, which is the production of grain of the city, amount of grain production. This is still an ongoing project, so there is chance that the Voronoi polygon you have seen, we will change it, because maybe we will need to take into consideration roads, which are not taken into consideration by this, or maybe we have to take into consideration also some kind of the distance, so that the farther you are, the less weight you will have being summed over the overall amount of wet that will arrive to the specific city. So given that, we've seen that if this is the grain population, this is the population distribution, they are not moving actually together. They're kind of sparse. In logarithm, if we have a log scale, it will be like a shadow. And even the network by itself does not explain well enough the population distribution. So it's not due to a network, and it's not due even just to the resources. So there should be something in the generative process, maybe something simple, something that we, like a very simple rule that we can get, and that we can extract, and we can actually simulate and see if we were able to reproduce that model. So the overall idea is that we were looking for a very simple rule that enables us to exchange. And the idea is to mutuate, not copy, but mutuate it from Gorg home. So if a difference of potential between two nodes depends on this resistance, and the flows of electricity depends on the resistance and of this resistance, we could do something similar. So we can get that, yes, the resource accumulation the new resources to trade depends on the previous resources, plus a fixed amount of accumulation that depends on how much grain or mines of olive oil you have there, and a rate of consumption which depends on the population. Fine, an accumulator. Then you see that the amount of trade from one city to another depends on the difference in the difference between the amount of stock, which is moderated by the traveling distance from the two cities on the seafaring network. So if it takes longer to go to one place to another, the exchange will be lower. Then we define a population growth which is exclusively due to commerce, so we exclude everything else. We just focus on commerce because we want to see if that thing, commerce and position, will be the main driver of the distribution of sizes of population cities during the Iron Age. And then, of course, we had this, and we put a diminishing rates for if they're not commerce at all, it will slowly decrease. And after all, well, Preliminary, we got a good result because when we tested, we compute the R-squares between the actual size of the population, the one that we have simulated, we compute a value that was around 68%. It was good for kind of model. I was surprised. And we got some population which has a very high error, of course, other which has less. There was some mistake, of course, but the variability was kind of expected because there are so many different elements. There is culture we're not taking into consideration. We didn't want to take into consideration. There are wars. There are earthquakes. There's a lot of problems there. So the problem with this that we have found with older data. So we are not using yet the right data, which are still working, actually we are working these days on these, but we ask ChatGPT to generate each data and we compare with the actual results that we have, like data from books, basically, if they make sense. And we tested that. The data we have are not far, will not be far from that. So we won't have that issue, but still this is a result that has to be taken with some consideration because we need to test it even with real data, which has not been done. Maybe a couple of weeks later, this seminar will be done, but not yet. So it's still a work in process. And okay, I'm pretty sure the time is gone. So there are many other things, but maybe is still a good time to stop and I will talk to you about behavioral sync in any other case. So thank you very much for your attention. And if you have any question, I'm around or here.
Okay, thank you very much, Francesco, for a very nice talk. Is there any question, comment? Okay, by order of...
Thanks, Francesco. I wanted to ask about this last part.
Okay.
You mentioned your motivation was to understand the rise of Carthage, but you use, if I understood correctly, data from the Iron Age.
I data from 1200 before Christ until 350 Annus Domini, after Christ.
Okay. Then you have the period where Carthage
Yes.
falls. Okay, and do you have some conclusion on Carthage? So was your hypothesis right?
Carthage is like high in population, yes. Even when the model does not fit, even in the cases where like you work at the beginning, I was working and not make it work and was not working properly. Carthago was in a position which doesn't have a lot of resource, but it's such a central position in Mediterranean, it all the time grows. Such as that the reason why now we don't have later I also study more because I didn't only do that, but I also study the specific point. The reason why we did not have Carthago now, we have Tunisia, is because the Arabs, when they in 1690s, invade that area, that part of Northern Africa, and they conquer Carthago. Then the Byzantines reconquer it with a fleet because they didn't have a strong fleet, Arabs. So to not make it have conquer all the time, they just destroyed and build Tunisia. So that's the reason why we don't have Tunisia there. Is a consequence of the fall of the Mediterranean trades.
Okay. Another question, like another city that did this a lot of falling and being relevant despite being conquered is Constantinople. Have you checked it?
Constantinople is not so high. It's pretty high, but not so high. Because if you check the Mediterranean, actually is at the end, is corner. It's strategic because of the Black Sea. But if you check the Mediterranean, it's a little bit close. First element. Second element, the city is not bad, is big, but not very big, because in 350, it was already a big city, but it was not big as 2 centuries later. It was at the beginning of the Constantinian renovation. So and it was not like so big during like it became very important at the end of the antiquity. At the beginning, Byzantium was never like Athens or Sparta or Corinth or Thebe or something like this.
Okay, thank you.
Welcome.
Hi. In the problem of the attraction of patients to hospitals, this gravity law has the dependence on the number of beds, a potential dependence on the number of beds, and exponential on the severity.
Yes.
Why? So, did you check other relationships? Why don't put both potential or both exponential? I mean, I'm surprised by the exponential dependence on the severity. Is there any reason for that? Any physical or biological reason for that?
The reason is that the higher is your severity, the more you will prefer a place with more beds, so a bigger hospital. So we could have done different. This was the one with highest fitness. When we got here, it makes some logical sense of what actually the expert of the field, because I know almost nothing now. I knew nothing at the time, and about healthcare management, of course. But what they actually explained me, yeah, of course, because if you are feeling very, very bad, you're going to the biggest hospital all the time. But if you are feeling not so bad, you're going to doesn't care if the hospital is big or not. So that ratio kind of encoded this sentence. So I thought, fine, it makes logical sense.
Yeah, but I don't understand why exponential. I mean, a potential behavior will do the same, but this is a worse fit, isn't it?
Is it?
It gives a fit which is not as good. Is this the?
It was not so good fit. Not so good
Okay.
fit. Yes.
Yes, I also had some questions about the model of the patients, because I mean, as far as I know, when you are very, very sick, you don't go to the nearest hospital with your foot, but you go with with an ambulance.
We have excluded the ambulance.
Okay, that was because obviously the ambulance will also do this kind of thing, but it's more informed than the there are two things. First, we are still recorded, so I'm not going to say about the decision making of that. If you stop the record, I will say that out loud.